Yes, can you see a screen? Yep, okay, great. Okay, so as promised, today is primarily going to be a help session. I hope now I hope that you've engaged with the project a little bit, enough so that you have questions for me and you have implementations, concerns / problems. I just want to reiterate that perhaps it's more straightforward than it seems. We're here to get you through it. As we discussed, we're not yet thinking, geez, this one may not even count. I'll get you there, because fundamentally we're just trying to implement like I wouldn't say grade school, maybe high school arithmetic on polynomials. Like, this stuff really shouldn't be at least the arithmetic among polynomials, it shouldn't be very sophisticated in nature. The factoring is, but like the arithmetic is not. And you don't really have a factoring task aside from like cleaning up the factoring algorithm. Okay, so let's talk about sparse polynomials. So I've been sort of checking out the EdStem as much as I could. I've been away this weekend, so I sort of promised my wife to like not look at my phone, but I was doing so anyways. And it seems one of the problems is people are duplicating the dense version and keeping too much of it. So you really shouldn't be if you're using a vector, you really shouldn't be indexing into it in any type of way, right? There is no relationship between the position of the term in the vector and the term itself. So like in a dense polynomial, you had a terms vector and its kth position held the term of degree k, right? So the algorithms that we're adding and multiplying sort of presume that. That all has to be thrown away. Like that should be what we call in computer science abstracted away somehow, right? So instead, I want to consider what will happen if we implement a sparse polynomial and just limit ourselves to like two operations, which you may see littered through your implementation already, and that is pushing something and popping something. Pushing generically means to add, in this case, a term to the term vector, and popping means to remove one. Now, in this context, if we want to add a single term to a polynomial, this would be done with the push abstraction, right? So as long as you have some type of push function that, given a polynomial in a term, will put that term in the polynomial, that's half of what we need. The other half of what we need is an ability to remove one term from the polynomial, and in fact, remove a very specific term. That is the term of highest degree, what we call the leading term, right? So as long as you can push a term into a polynomial and remove a term from a polynomial, which I'll say pushing and popping, implementing addition should be quite straightforward. Now, I'll try to demonstrate this. So first, let's presume that you do in fact have a function push that, given a polynomial and a term, will simply output p plus t, right? And I'm going to show you don't actually have to implement push and pop, right? Like utilizing the heap data structure. But if you don't want to engage with the heap data structure, here's like sort of the pseudocode of what has to be accomplished. So in order to push a single term into a polynomial, you need to extend. So like, I'm presuming you have some attribute in your structure called p dot terms, where you're like holding a vector of terms. So if you want to push a term into that, you have to extend that term vector by one cell and then insert t into it while maintaining order, right? So you can either like order them in ascending degree or descending degree. But what this means is that you have to sort of like walk through your vector, figure out where it goes, and then move everything down a bit. Or you can just make it the last thing in the vector and run sort. It's a little bit more expensive, but like only by like a tiny bit. These lists are very short. So like inserting is an ON operation, linear operation. Sorting is n log n, but like our lists are tiny, so that log n is going to cost you basically nothing. Okay, so how do we pop? This means, given a polynomial, how do I remove its leading term? Which essentially means, how do I take p and subtract its leading term of p from it? And push sort of was just a mutation operation. It didn't actually return anything. Pop is going to do two things. It's like going to mutate and return something, right? So if when I pop from a polynomial, it gives you the leading term, and the polynomial that you passed in will have its leading term removed. Okay, so this requires, and like a lot of problems in the EdStem are also not dealing with edge cases properly. Specifically, there's a lot of zero detection that has to occur. You got to be careful. So if I give you P and I say pop from P, first, if it's the zero polynomial, you just return the zero term. Like you don't do anything, right? This is sort of a special case. You can like continuously pop from zero, and you keep getting back 0, 0, 0, right? Because the leading term of 0 is 0, and 0 minus 0 is 0. Okay. If we don't talk about that degenerate case, we pull the leading term out of the p.terms attribute. It's either going to be in the first position of terms or the last position of terms, depending how you've organized it. And then you just have to delete the empty cell somehow and return the leading term. But again, I wouldn't actually recommend that you would do it this way. And I'm going to show you how to use heaps like right after this. Okay, so supposing you have that push operation and that pop operation, just suppose it's working. Here's the pseudocode for like implementing sparse addition on here's how you implement addition on sparsely represented polynomials. And as you see here, I'm never going to index into p.terms, right? You should just make that agreement when you start programming this to say, look, if in my addition operation, I'm indexing terms, I'm doing something wrong, because I should never require that. Because let's walk through this and ask what we have to do, or let's think what we would do in high school if asked to add two polynomials together, right? We would just sort of say, if we had f and g, if the leading term of f is the same degree as the leading term of g, we'd sum those terms, then remove them, and then move on to the next two terms. If the leading term of f was larger than the leading term of g, well, we just take the leading term of f, right? That's the first summoned in H, right? So we just sort of have to like implement this procedure with code, and it sort of looks like this. So here's, this is pseudocode. I didn't want to like write the Julia code for you because that's kind of like your task, but this is like one step away from Julia code, right? This is called pseudocode. I had an Italian friend who thought it was pronounced persuado code, and to this day that like I really find that entertaining. Anyways, so if you give me two polynomials p and q, and remember both of these are structures which provide pop and push, I'm going to output from this algorithm p plus q. Okay, so the first thing we want to do, so I said pop and push are like functions that mutate, right? So the input p and q are going to be destroyed, and you may not want to destroy your input. So what we're going to do is copy them, and you may have to deep copy, right? Because p and q are going to be a vector of terms, and terms are going to be references. So this really means deep copy. Okay, we're going to then form the answer, that is the sum of p and q, and then return the answer. And here's how we like construct it. While p prime is not 0, so p prime is just the copy. I may just say p and q, right? While p is not 0 or q is not 0, there's something to do. There are terms left. Okay, so what are the three scenarios that we can be in? Well, either the leading term of p and q are equivalent, either the degree of p and q are equivalent, or the degree of p is strictly greater than q, or the degree of p is strictly less than q, right? That's comprehensively all of the possibilities between p and q. Like, agree? Okay. So first condition, the degree of p is equal to the degree of q. That means their leading terms have the same degree, and therefore we have to combine these leading terms, right, before adding them to H. So I'm going to say the leading term of p is what you get when you pop the leading term off of p, right? And then p sort of is less, right? This also subtracts the leading term from p. I'm going to pop the leading term from q, and then q sort of becomes smaller, right? Q becomes q minus the leading term of q, and I'm going to hold them in leading term of p and leading term of q. I'm going to add the leading terms of p and q together, right? Using the term addition, right? Which is defined. You don't have to redefine that, right? That's handled for you. But you have to check that they're not zero, right? They can be zero. Plus x minus x gives you 0x. A lot of people are missing this, right? So if they're zero, you don't do anything, right? Those terms have canceled, right? And you just throw them away and you go to the next iteration of this loop. Okay, provided that they don't zero out, then you just push into the answer the leading term of p plus the leading term of q, which at this point is guaranteed to be not zero. Savvy? Okay. If the degree of p is greater than the degree of q, you just push the leading term of p into the answer. Otherwise, you push the leading term of q into the answer. And that's it. This will work. If you just implement this faithfully, if your push and pop routine works, if you make sure to like deal with these edge cases, right? Because you have to, funny things can happen, right? When you keep producing zeros. And this is most of what you need. Okay, furthermore, I wouldn't actually recommend you implement push and pop. There is a function, or there is a data structure. I hope this is installed. Perfect. Okay, there is a data structure in Julia already called a heap. I don't really want to explain to you like what a heap is. It's very interesting, but essentially why we want to use it, like push and pop are terminologies that come from heaps, right? We're sort of misusing them when pushing them and popping them into vectors. Like the nomenclature comes from a heap. So I'll give you an example of how heaps work in Julia. So you just get what we call a max heap. There's two types of heap. One where like you have quick access to the largest element, and one where you have quick access to the smallest element. In this case, we want our measure of largeness is term degree. So in this case, we want quickest access to the largest thing in the heap, right? Term degree. Okay, so here's an empty heap, H. I'm just going to push 1, 2, 3, and 4 into it. And it provides us this interface. I can ask for what's the first thing in H, and it's going to say 4. Then I can pop H, which means it gives you 4 and removes it from the heap, right? So now if I look at the first thing in H, it's 3. So I can pop again, and it gives you 3. And I can continue popping 2, 1, until it becomes empty, and you'll get an error. Right, so you just have to be careful not to try to pop from an empty heap. Okay, in addition to push, pop, and first, you get length is empty, first, and extract all. This is if you want to convert the heap into a list. Does anyone know what these bashes or bangs are used for in Julia?
When you're going to edit something.
Yes, so this is a naming convention to indicate that one of the inputs or more are going to be mutated, right, by the command, right? So when I give it this heap H and I call push, H is going to change, right? So this exclamation mark is just denotes that. Okay, so any ideas about how we can utilize this for our like sparse polynomial arithmetic? Like, so what happens if you make your terms attribute a heap? I said what we need to be able to do is push a leading term and pop a leading term. So how should we order into the heap, right? So this was ordering by like the ordering on integers. So what kind of ordering do we need for terms? By degree. So it turns out that this is already defined though in your Julia file. We've already defined for you the comparison operator for terms. You don't even have to write it. This means that heap's going to work out of box with terms. There's like nothing left to do. So here's a binary heap. I'm just going to put terms in them. What's its first one? Right, 4x to the 4. And look, I didn't give it in order. Right? Can I pop H? Yeah. Here's the leading term of that polynomial. All right, can we push a term into it, right? 1 of degree 10, sure. Well, what's going to pop now? 10 to the 10. What's going to pop next? It's the 3, right? And then it's the 2, and then it's the 1. And then it will be empty if I try that again. Okay, so let's review, right? I said, provided that you have a polynomial, which provides this pop and push sort of interface. And all you have to do is implement this for add. Right, so I think most of the struggling with sparse polynomial addition is the insistence of indexing into the term's attribute, because we're too close. We're trying to too closely duplicate what was in the dense arithmetic. Right, so you should do that. Like, what time is it? We have plenty of time. Like, you're going to be able to do this before you leave the hall, surely, especially with Yanni and I's help. So is there any questions regarding that? You can always ask me again if you're struggling to put it in. Okay, so that's the first implementation hint I have. That's the second. That's the third for custom ordering. Okay, so for most of you, you're probably not going to attempt some of the bonus tasks, but if you're going to attempt one of the bonus tasks, I just give you this caution. When you're doing Chinese remainder theorem, if you choose a prime, which reduces the degree of the polynomial you're trying to factor, that will break everything. This is called a bad or unlucky prime. Okay, there's like a theorem that says, if I factor a polynomial mod f, it should have at least as many roots as when I factor that same polynomial mod p. And here's an example, right? So this one clearly has 2 roots, a fifth and 2. It's 5x squared minus 11x plus 2. But if I take the same polynomial mod 5, it becomes 4x plus 2 and it has 1 root. So that will really mess with things. So just keep this in mind if you're trying to implement that bonus task, that you have to discard primes that divide the leading term of your polynomial, or you're going to get like really weird results. Okay, what else did I want to talk about? Back to the Chinese remainder theorem. Where did it go? Sparse content factorization, more. That was division. That's multiplication. Where did I just state it as a? Okay, Chinese remainder theorem. So we can really focus on just the Chinese remainder theorem with 2 m's, right? It's not really necessary to like do it for k many m's. So you really only have to understand like the first 2 lines of this Chinese remainder theorem. Like, so suppose I have like a secret number, and you can ask for its modulus m1, and you can ask for its modulus m2. Right? The only precondition is that m1 and m2 are coprime. Right? They can't share any common factors. So if you just forget about like everything here on in, right? I'm saying the secret number can be constructed by u is equal to v1 plus v2 m1, where we're going to construct v1 and v2 in the following way. Like, so the first thing I want to recognize is that this, right, modulo m1 is just v1. Right? So clearly u1 is equal to v1, and then we just assign u1 to v1. Right? So now I have v1. So how do I get u2? Well, u2 now is this whole thing, right? Mod m2. If I have v1, I just have to reorganize this equation, and I get v2 is u2, which is known, minus v1, which is known, and the inverse of m1 mod m2. And in order to get the inverse, the only thing required for Euclid's algorithm is that m1 and m2 are coprime. Right, so it's not necessary to understand how this works for k. If you could just understand it for 2 pieces, right, that's sufficient. Right? Because indeed, that's all I'm asking you to do for the Chinese remainder theorem for polynomials. Okay, so so just keep that in mind, right? Given a magic number that's secret, and you have its images modulo M1 and M2, which are coprime, it's actually quite straightforward to recover M, right? Based upon these two equations, right? So you get V1 by this and V2 by this, and then U is just V1 plus V2 M1, right? Very straightforward. Okay, so let's go down to the Chinese remainder theorem down here. Okay, so what I'm asking you to do here, right? Okay, so when you implement your big integer arithmetic, you should find that everything is like really slow now, right? Doing arithmetic on big integers is a lot more expensive than doing arithmetic on 64-bit ints, right? So that should flesh out in some of your testing examples. So how we're going to mitigate this is we're going to perform a big integer, perform a multiplication with polynomials with big ints by doing a bunch of polynomial multiplications with the coefficients being like regular ints. Right? And we do it in the following way. Right? So you just pick a bunch of primes, and the primes have to exceed some threshold, right? And the threshold is given here. So it's the height of A, that's the largest coefficient, the largest absolute value of the coefficients of A and B, and then multiplied by the minimum number of terms of A or B, right? Which you can just basically use the degree, right? You don't even have to really count the terms, right? The degree of A and the degree of B is going to be strictly larger than or equal to the number of terms it has. So you have two, you want to multiply A by B, and you want to get this, right? So this, strictly speaking, isn't known, right? And it will be expensive to do this. So what I'm suggesting instead is you pick a prime like 5. You do the multiplication mod 5 and you get the product. You do the multiplication mod 7 and you get the product. And then, like, and this table sort of doesn't demonstrate this, right? You should then like use Chinese remainder theorem. Like, I don't want you to do Chinese remainder theorem on 3 polynomials. I want you to keep like updating, right, one polynomial, right? Because I said we don't need to do Chinese remainder theorem on K many mods. We just need to be able to do it on 2. But if you can do it on 2, you could do it on K, right? Because you just do 1 and 2 and combine them, and then you add 3, combine it, 4, combine it, right? So that's what I want you to do here. So you do it for 5, and then you do it for 7, and you combine it, and then you do it for 3, and then you would combine it, and you would keep going, right? Until these primes, the product of these primes have passed your threshold. So indeed, that's what I have outlined for you here. So I said, here's the Chinese remainder theorem. Given 2 polynomials, A and B, such that, so it's okay, I have to state this properly. A and B and NM. Did I write this correct? Like I think A and B are like the same polynomials, just their images. A and B and N and M, such that A is in Zm and B is in ZMX, and the GCD of NMN is 1. Yes, okay. Okay, so like, remember the integer one. Like I'm saying, I have a secret number, and I'm going to give you 2 images of that number, and you reconstruct the main number. So we just have to like do the same thing with polynomials. So I'm saying there's a secret polynomial, right? So that has big int coefficients, and I'm going to give you like 2 polynomials that are like the image of that when you take a mod, right? So one of them's mod n, and one of them's mod m. And this is the Chinese remainder theorem for polynomials, which will combine those 2 polynomials together, right, and give you its image C, such that C is congruent to A mod M and C is congruent to B mod M, right? So it's just like an analog of like the integer one, but with polynomials. And all that's required here is for you to look at all of the coefficients, right? If you like look at all of the coefficients, you sort of like vectorize it. You have all the coefficients of A, all the coefficients of B, right? And then you just perform Chinese remainder theorem on each of the positions, right? The first position, the second position, the third, and you generate like a new term vector, and that will be the one for C, right? So should be pretty straightforward to implement this, right? And you should use this as a usage example, right? You should work out, updating 7 with 5 and 3 with 5. I don't know why I ordered it this way. You should go from 3 to 5 to 7. And then once you do that, you just sort of use like the Chinese remainder theorem on 2 in a larger algorithm where you're just like combining 2 and then getting another one and combining. So let's look how this works. So given A and B, right, they have big integer coefficients, right? So when you see ZZ like this, like you need to think really the integers, right? Which means that they have to be big integers. ZP in your mind, you have to think of as sort of regular machine integers, right? That's the interplay here. So you get the height of A, you get the height of B, and you just have to sort of scan through all of their, all of the terms and find the biggest coefficient by absolute power, find the biggest coefficient while taking absolute versions of them. This is going to be your bound, right? So it's predictable how many primes that you're going to have to choose, or like it's predictable how many primes you have to multiply together because they have to exceed B. And I'm just saying, okay, pick the first prime. It's 3. The current M that we're working with, right? So that's going to be the mod M part of the Chinese remainder, right? Gets P. So at this point, it will be 3. And then you just do A times B mod 3, right? That's like the first multiplication that what you want to do. And from C, we're just going to keep using Chinese remainder theorem on 2 polynomials to like keep going, right? Now we're going to get the one of 5 and combine it, then 7 and combine it, and 11 and combine it, right? And it's going to keep, it's the coefficient field is going to keep growing, right? To like include 3 things and 15 things, then 3 times 5 times 7 things, until it's so large that it's actually the answer in the big integer version. Right, so while M, which is the current sort of modulus you're working by, is less than the bound that it needs to be, just generate the next prime after P. And like Julia has next prime, this function. You just have to, I think we discussed this last like counseling session. Who was there? It's definitely included in Julia. I think it's just in like the number theory package or something like that. But you can just go utilize this next prime. Although it's kind of weird. Next prime of 3 is 3. Right, so it gives you the next prime equal to or greater than the thing that you give it. So if you want the next prime after 3, you actually have to give it 4, and then it will give you 5. I just thought that was kind of strange behavior. All right, so you get the next prime. Then you get a new C, right? So you do A times B mod P, which is going to be your fast multiplication over ZP. And then you use the CRT algorithm you wrote that's able to combine exactly 2 polynomials to update C. Then you update your M. And then you just repeat this again. If M is not sufficiently large, then do another product and then update. Right? And if M is not sufficiently large, and then you continue. And then afterwards, all we're asking you to do is restore negative coefficients by using this symmetric mod, for which there is an explanation here. In fact, here's the symmetric mod. Right? That's all you have to implement. Right? It just does a shift so that instead of going from say 0 to 6, we're going from like -3 to 0 to +3. Okay, what else did I want to say? Okay, so like questions now. That's really only the 2 pushes I wanted to give. Did you guys want to start working now, and then I'll come around and like give individualized help, or is there anything else that I could like clarify or push you in the direction of? Okay, so get to it. Chats. Oh, I can't see the pseudocode for the CRT on GitHub. You can't. Really? This Jupyter, no, I just pushed today. Like,
The cells, it's just, it doesn't have.
oh, sorry, that, yeah, wasn't my intent at all. My intent was for you to have it. I had no idea that it wasn't showing up on your end. How can I, okay, can I print this? Okay, I'll try to, okay, I'm gonna try to print a PDF copy of this. Let's just see if it will be included. Sorry, I had no idea. That's quite bizarre.